Welcome back, everyone, to our ongoing exploration of the OEIS. If you're working with number theory, you definitely know the online encyclopedia of integer sequences. It's just invaluable.
Absolutely essential. A real treasure trove.
Today, we're zooming in on one particular sequence, A000232.
Ah, yes. A000232. Doesn't sound like much, perhaps, but, well, the story behind it is quite something.
Exactly. The OEIS description is, let me read it, construct a triangle as in A036262. Sequence is one less than the position of the first number larger than 2 in the nth row. Nth difference.
Okay, that's a bit of a mouthful, maybe.
Yeah, a little dense. But the key thing, the thing that makes this interesting is what it connects to. The OEIS comments mention it's related to Gilbert's conjecture.
And that's where things get really fascinating. Gilbert's conjecture. It sounds so simple, but it's one of those problems that's just, well, stubbornly unproven.
So let's unpack that. Gilbert's conjecture, what is it? It starts with the primes, right?
That's right. You take the prime numbers, 2, 3, 5, 7, and so on, your first row. Then for the second row, you take the absolute differences between consecutive primes. So 3, 2, 1, 5, 3, 2, 7, 5, 2, 11, 7, 4, giving you 1, 2, 2, 4, 2.
Absolute difference, meaning always positive. Got it.
Exactly. And you just keep doing that. For the third row, you take the absolute differences of the second row. 1, 2, 1, 2, 2, 5, 2, 4, 2, 4, 2, 2. So 1, 0, 2, 2.
And you build up this triangle of numbers, row by row. This is the Gilbert triangle.
That's the one, sometimes called the Gilbert difference triangle. And the conjecture itself, proposed by Norman Gilbert back in 1958.
Yes.
It's simply this. After those first two rows, the very first number in every single subsequent row is 1.
Every single row. Just one.
Just 1. Every time. It's a really striking pattern when you see it.
Huh. Now, you said Gilbert in 58, but I think I read somewhere, someone else noticed it earlier.
Oh, you're right.
Yeah.
Francois Proth, actually, back in 1878. He spotted the same pattern. He even tried to prove it, but his proof wasn't quite correct. So it's mostly known by Gilbert's name.
Interesting. And Gilbert himself, he wasn't purely an academic mathematician, was he?
No, that's another fun part of the story. He studied math at UCLA, worked at Rand Corporation, but he was also a magician. Invented card tricks, like the Gilbert shuffle, which, believe it or not, has mathematical underpinnings itself.
That's fantastic. Math popping up in unexpected places. Okay, so this conjecture. First term is always 1. Simple to state. Hard to prove.
Extremely hard, apparently.
Yeah.
It's been verified computationally for, well, an incredible number of rows. Andrew Udlisko, in 93, pushed it out to something like 3.4 times 10 to the 11 rows.
Wow, 340 billion rows, and the first term was still 1.
Still 1. That's pretty convincing evidence, you might think.
You'd think, but still no proof.
Still no proof. It remains a conjecture. Which brings us back, finally, to A000262.
Yes, and A036262 in the OEIS is precisely the Gilbert triangle we've been talking about, generated from the primes.
Okay, so A000232 is derived from that triangle. The rule was 1 less than the position of the first number larger than 2 in the nth row. Exactly. So let's take an example. The sequence starts 3, 8, 14, 14, 25. For the first term, N1, we look at the second row of the Gilbert triangle. Remember, that was 1, 2, 2, 4, 2.
Right.
What's the first number in that row that's strictly greater than 2?
Okay, 4.
And what position is it in? It's the first, second, third, fourth number.
Fourth position, okay.
So the rule says the sequence term is 1 less than that position. 4 minus 1 equals 3. And that's the first term of A000232.
I say, let's try the next one. N2. We look at the third row. That was 1, 0, 2, 2, 2, 2, 2, 2, 4.
Right. So scan along that row. What's the first number you hit that's bigger than 2?
Again, it's a 4. Way at the end there.
And its position. If you count it out, it's the 9th number in that row.
9th position. So 9 minus 1 is 8, which is the second term, 3, 8. Okay, that makes sense now.
Precisely. So as A000232, it's basically telling us for each row of the Gilbert triangle, starting from the second row, which corresponds to N1 for the sequence, how far we have to go into the row before we find a number bigger than 2.
It's like a measure of how long the initial run of small numbers, 0, 1, 2, lasts in each difference row.
That's a good way to put it. And if Gilbert's conjecture is true, the first number is always 1, so we know we're never going to find something 2 right at the start. We always have to look at least one step in.
So the behavior of the sequence, how fast it grows maybe, might tell us something about the structure within those difference rows.
Potentially, yes. It's encoding information about where these slightly larger differences first appear. Now, people have wondered if this Gilbert property is special just to primes.
You mean, could other sequences work?
Exactly. Hallard-Croft suggested maybe sequences starting with 2, then odds, if they didn't grow too fast or have gaps that were too weird. Turned out, No, counterexamples were found. It's not quite that general.
So it's pickier.
Seems so. Lisco had a slightly different idea, maybe sequences starting with one and even numbers if the gaps were sufficiently random and not too big.
Sufficiently random, that sounds hard to pin down.
It is. It's not a formal definition, more of an intuition, but it suggests the structure, or maybe the lack of certain structures, in the gaps is important.
It makes you appreciate the primes even more somehow. There's also this other related idea, isn't there? Gilbert permutations.
Ah, yes. That's another fascinating tangent. A Gilbert permutation of numbers 1 to n is a reordering where if you take the first, say, j numbers in the permutation, you can rearrange just those j numbers to get a block of j consecutive integers.
Okay, that sounds abstract. Is there a concrete example?
The classic one is the connection to a card trick. Imagine a deck setup alternating red, black, red, black.
Standard setup.
If you cut the deck anywhere and then do one perfect riffle shuffle.
Which is hard to do perfectly, but okay.
Theoretically.
Mm-hmm.
The resulting deck still has the property that consecutive pairs of cards are different colors, red, black, or black, red. That property relies on the underlying sequence being a Gilbert permutation.
Wow, okay, that is neat. From number theory conjecture to card tricks.
It shows the connections, right? And people have even defined Gilbert numbers using these permutations in continued fractions or decimals. The math goes deeper. Repeating Gilbert's continued fractions, for instance, relate to quadratic irrationals.
So it connects into algebraic number theory, too? This thing has tentacles?
It really does.
Yeah.
And more recently, there's work by T. Agama, who's tried to reformulate the original conjecture using ideas like gap sequences and paths and traces based on the prime sequence.
Trying to find a new angle on the problem.
Essentially, yes. Providing a different language, maybe a different structure, to analyze why that first term might always be 1. His reformulation connects the conjecture to properties of these paths and their traces.
Does that make it easier to prove?
Well, it offers a different toolkit. Whether it makes it easier remains to be seen. It's still unproven. Paul Erdones, the famous mathematician, apparently guessed it might take 200 years to prove Gilbert's conjecture.
200 years. Oof.
Yeah, he apparently called it a strange thing to study, but also suspected it might link to really deep things, maybe even the Riemann hypothesis, because it's fundamentally about the distribution of primes and their differences.
That's the thing, isn't it? These simple-looking questions in number theory can just open up into vast, challenging landscapes.
Couldn't have said it better myself.
So let's recap. OEIS sequence A000232, our focus today, it's not just some random string of numbers.
Not at all. It's intrinsically linked to the Gilbert triangle, which is built from the prime numbers.
And specifically, it tells us about the position where the numbers in the rows of that triangle first jump above 2.
Right. It gives us a specific numerical lens onto this pattern, described by Gilbert's conjecture, the unproven idea that the first term in the difference rows is always 1.
A conjecture that looks simple, has massive computational support, connects to card tricks and deeper math, but still resists proof.
A perfect example of the allure and the difficulty of number theory.
So here's a final thought to leave you with. Could studying A000232 itself offer a new path forward? We know what it measures. Could its properties, its rate of growth, maybe patterns within the sequence itself somehow constrain how the prime differences behave? Could this sequence hold a subtle clue needed to finally crack Gilbert's conjecture?
That's the tantalizing question, isn't it? Maybe looking at the sequence isn't just descriptive. Maybe it's prescriptive in some way we haven't yet understood. Definitely something to ponder.
Absolutely. It shows how even a single entry in the OEIS can be a gateway to profound and unsolved mathematical questions. Go take a look at A000232, explore the Gilbert Triangle yourself, and see what you think.